So friends, we have been talking all along that data is very important for probabilistic risk assessment, and when we say that, we should know how the data, whatever we have collected, whether it is a failure data or a frequency data, how well they can be represented so that quantification is adequately done. This is where the probability distributions they have come. They are very, very fundamental to data analysis. So let us see what are the different probability distributions. Distribution and key probabilistic metrics. Statistical distribution is part of science, and they are very important that we know that distributions present salient features of population. It is the distribution which gives us, in fact, in probably PRA or it is machine learning. Machine learning, there is a very important step. It is called feature extraction, and in feature extraction, the population is not fed directly. It is the population characteristics in terms of mean, median, or key parameters. It is fed, and like if it is a vibration, RMS value, these are the parameters that are fed, and that is where the time domain, frequency domain data, they are very important. So distribution play a very important role in statistics as part of AI and ML algorithm, and in PRA also it plays a very important role. Because we want a organized data, and that is where we fit failure rate. It is the you know that this cap lambda. It is a maximum likelihood estimate. We'll be discussing that actually. So these kind of features we require for our distribution to get estimate of the population. Okay, major metrics as a mean, standard deviation. There are two broad category of distributions: continuous and discrete distribution. Continuous distributions are real numbers having continuum of values. Okay, and discrete distributions, they are having an integer value, like 3 failures, 2 failures, 5 per persons. Like these are discrete values. So these two values have to be represented. So continuous distribution and discrete distribution, there are two major categories. And common cause failure models a key parameter without which results tend to be optimistic or redundant configuration. Importance analysis, since I am giving you the metrics, it is very important we don't leave these things. Common cause failure we have discussed in previous lecture, and important measures, that is identifying these things, that also we will discuss, but later on in the presentation. Now continuous distributions, typically if the value of interest is in the form of 1.1, 5.7, 3.4, then they are unlike discrete numbers 1, 10, 15, 20. So then we have a continuous distribution. Uncertainty characterization is inherent part of distributions actually, because every distribution, like let's say log normal distribution, normal distribution, the distribution upper bound, lower bound, they characterize the uncertainty. So distributions are also very useful for characterizing the uncertainty in the data or its results. Graphical representation of the data enable us to have a better perception, the kind of data that we are having, because normal distribution, it's a one of the most sought after and used distribution, wherein it is also called symmetrical bell shaped or Gaussian distribution. So this distribution is used a lot in quality control, manufacturing industries, where there are chances that data will has equal probability to fall either on positive side or negative side. And the scope of the lecture deals with the normal, log normal and exponential distribution, because these distributions are used in probabilistic modeling more compared to any other distribution. So, you have a choice to study other distribution on your own if you are interested. But then if you have one distribution understanding and all that, you can definitely adopt other distribution. In fact, I would talk about the viable distribution also that we have covered here. So, normal distribution, this distribution was discovered by de Moivre in 1773, and by giving a curve and the astronomical data that it represented, and the distribution is also referred as Gaussian distribution. Okay. Typically, you can see it looks like this, and then it has got sigma value. So, normal distribution is characterized by mean and standard deviation. Standard deviation gives spread of the area, that is sigma, 3 sigma, 2 sigma and single sigma. So, on this x-axis, okay, and then normal value, mean value. So, it is written like n mu sigma, okay, and then what you have on y-axis is probability density function. It is written as Ft, and its model Ft is written like this: 1 upon sigma into under root 2 pi. The line is coming up to covering 2 pi number, exponential minus 1 by 2 t minus mu upon sigma is a some way of representing the spread, and then square, and this is a Ft, that is probability density function of normal distribution, can be read as follow, and it has got a limit from minus infinity to plus infinity. That means theoretically it does not reach 0 actually. Okay. This is what we are trying to say here. So, once we have a probability distribution PDF distribution over here, then the second thing, cumulative distribution function CDF is formed. What happens? What is the area covered under up to here? We linearly go on adding it. So, we know that total area under the curve is 1. So, till this thing, this line cumulative distribution function, the way name suggests it, when it reaches 1, then we call CDF of normal distribution. Okay. So, and this is more important than this, because in reliability we talk about the either reliability, that is R as a function of t, and failure probability f as function of t. So, here we are talking about f as a function of t or any variable that we are trying to have it. So, here also t, so we can say this will be t. So, cumulative distribution function, the characteristic is finally it reaches 1. If we arrange the data in ascending order, and if we give ranking to one first data, second data, third data, ninth data, 9 out of 9, it will be 1 only. So, that is how it is cumulative distribution function is 1. And the second distribution is log normal distribution. If the log of any variable is like normal value, then it can be said it is a log, it is following a log normal distribution. Okay. So, this is where we have this sigma value, how it characterizes the shape of the distribution. Here sigma is equal to 0.15, sigma is equal to 0.3, and it is 0.5. So, you can see log normal distribution can be characterized by a skewedness on one side. Okay. Normal distribution, it is equally distributed, it is more like a normal distribution when sigma is 0.15. But if the spread is more, then it behaves like a skewed distribution, and that is the characteristic of a normal distribution as it looks to the optics, and we can say this is so log of any value, and that it follows, it called log normal distribution. Log normal distribution is extremely used in representing failure data. In probabilistic risk assessment, data coming from various sources, they sort of shows independency. So, then we have if you plot this data, they will be fitting on the log normal curve. This is the experience it suggests, and that is how log normal distribution is used more in probabilistic risk assessment, because as I said, the error factor, that is ratio of 95% confidence level to the median value, and log normal distribution does not give you mean, it gives you median value. So, that gives the error factor, as I have written 90% confidence, that is 90% 5% bond divided by median is called error factor, and this error factor along with the median value is used in simulation in the fault tree. So, that is how the log normal occupies more importance in probabilistic risk assessment. Error factor of 3 is considered okay, but if there is an error factor of 5 or so, like for human reliability modeling, then it is to be thought about actually. Okay, then exponential distribution. This is the very elegant simplistic distribution. Its formulation also is very simple because it has got one parameter, like log normal there are 2 parameter distribution. This parameter is and its parameter is lambda. So, if I express reliability e raised to power minus lambda t. So, lambda is the parameter of the distribution. So, and we know that reliability plus failure probability is equal to 1. So, reliability 1 minus failure probability, that can be written, as I have told you, Ft is obtained in previous slide, cumulative distribution function. So, you get the reliability estimate, this matrix also you got the answer over here actually. And then the above makes it practically modeling application very simple, because if the distribution is complicated, like we have normal distribution, we need to use a table where a standard normal distribution is created, where mean is 0, and then this sigma, like plus 1, 2, 3, like that, it represents a z value. So, probably I will show you in some slide how it works actually, but if you see the reliability estimate exponential minus lambda t, it is most elegant and most effective way, because most of the time we are dealing with the time domain t and the failure rate lambda. Okay. And then here I am expressing Ft is equal to 1 versus what we have derived from here, and what CDF is we got Ft, if you integrate from 0 to t, you will get the failure probability. So, it is a connection between previous slide and this slide that we have over here, okay. Then this distribution does not have memory, because for example, failure probability of 2 components, one that has operated for a period of t, time t, and another that has just been put into service in time domain t, will have the same period t plus delta t. Okay. From that instant of onwards, we will have that value in consideration. So, it does not have a memory actually. In short, the distribution does not capture aging. Okay. And that is why this exponential distribution is also called as constant failure rate distribution or constant hazard rate distribution. Okay. So, here we have this hazard rate. Hazard rate is nothing but ratio of Ft upon reliability. Okay. Hazard rate is Ft is lambda exponential minus lambda t divided by exponential minus lambda t, and we get and this is a constant. So, this is also called constant failure rate or constant PDF distribution actually, constant failure rate distribution or constant hazard rate distribution. Okay. Probably if you want to understand hazard rate, I can give you example of on a ship, you are carrying so many components, like n number of component, and then over a period of time you consume some component. So, hazard rate goes on increasing because we are not having inventory, and so it affects the risk is associated more if you are talking about the component availability is concerned. So, probably you and of course, mathematically it is very simple, PDF of t divided by reliability as a function of t, and that is how lambda is constant. Now, Weibull distribution. Weibull distribution is, I would say, is basically king of the distribution, at least in PRA. Why? Because once we have a Weibull distribution, we plot the data on Weibull and it can inform us which distribution our data follows. Like I'll be showing in the slides. So this distribution basically is three parameter distribution. You can see alpha, theta and beta. Alpha is called characteristic life, beta is called shape or slope parameter, and theta is called the point of starting. Okay. So that is location parameter. Okay. So if it read like this, fx, x could be t. So we are talking about x here. Beta divided by alpha minus theta, x minus theta, alpha minus theta raised to power beta minus 1, exponential x minus theta, alpha minus theta with the minus sign raised to power beta. If I see as a two parameter distribution, if I remove theta, so beta upon alpha, x minus alpha beta minus 1 exponential x minus x upon alpha raised to power beta. So this is a simplistic form in two parameter distribution we have. This distribution is used in life testing studies a lot, and indirectly in a physics of failure model when we create, this distribution is very common. Now you can see the Weibull plot of three parameter distribution. Beta is equal to 3, alpha is equal to 1, beta is equal to 2, and beta is equal to 1 is basically like an exponential graph you can see here. So in probability paper also we can see this distribution. Okay. So we know that. Now we got PDF, and if we integrate PDF, we will get the fx, ft is equal to 0 to x, then PDF integration, and we have dx. So if we integrate and this thing, so we will get finally these are the inherent steps. Okay, and we get cumulative distribution wise 1 minus exponential, that is failure probability is equal to 1 minus exponential x upon minus x upon alpha raised to power beta. Okay, and this is the equation for CDF of the Weibull distribution. In the above equation, when x is equal to a, it follows. Okay, 1 minus this thing. So almost like we are writing a, when x is equal to a, then we get the characteristic life. It reduces to 1 minus exponential minus 1, and finally we come, this is 63.2. So for a characteristic life, when x is approaching a characteristic life, the 0.632, that is 63.2 failures would have occurred, and when it reaches 1, all the failures would have occurred. So that's why this 63.2 or 0.62 occupies a special time, because a line drawn from on Weibull plot from 63 to 0.2 on the cumulative distribution graph to x-axis, and then it will give a alpha value, that is 63.2, and y-axis will get that probability. Now we have the discrete distribution. Discrete distribution is basically when we are talking in numbers actually, and we will also know that how we can if we talk about binomial distribution, and so we consider an experiment of n trials. Okay. So this distribution is used more when we talk k out of n, 2 out of 3, this combination, failure or success. You want to evaluate the probability. Let's say what is the probability of 7 pump you have provided somewhere in the sequence, and what is the probability that 2 pump will fail. Okay. So out of 7, 2. So how you will estimate that probability, because it goes into the permutation combination domain for estimating that probability. So we have n is our population, as I said 7 pumps are there total, and then we have the outcome is discrete, that is success or failure. Okay. Suppose the number of success event is x with a probability p. Please notice this. Suppose the number of success event is x, that means 2, 3, 4 cannot be more than whatever 7 we said, and the probability is P. Then this also implies that number of failure event is n minus x. We are talking about success domain, so failure domain will be n minus x, having probability 1 minus P, because we are talking of P as the success probability. So 1 minus P will be failure probability, denoted by Q. Okay. The PDF for binomial distribution can be described as, so we said probability of x success, n is the population, and P is the probability for each event. Okay. So PDF can be given by n of x, the and probability of x success. Probability is associated with the success, and failure is associated with n minus x. So this is a simplistic distribution where we have only two states, success and failure, and n is 2. The population is 2. So we'll have how many? 4 probabilities. Either both will be success, one success, one failure, one success, and both the fails. So this is the permutation combination we get. So the matrix become P square plus 2PQ plus Q square. So this is nothing but A plus B whole square. So P plus Q whole square, that terminology we got. Now on the similar lines, we go for the n is equal to 3. So again we can draw this matrix. This we are doing to derive the expression for this binomial distribution. Okay. So PPP all success, one failure, two success, one failure, and various combination we draw. So we get P cube, okay, and then Q cube from here, and in between term 3P square Q, 3P square Q, okay, this one also, and 3PQ square, this term. So again this is a PQ plus 3P square Q plus 3PQ square plus it is nothing but P plus Q raised to power 3. Okay. So what conclusion we draw from here is like this. That is how we see the binomial distribution. So Fx is equal to n upon x, P raised to power x, and Q n minus x. This is the binomial distribution that we get in the final form. Now let us see what is the Poisson distribution. Poisson distribution is a little bit like, you know, when we are dealing in population wherein let us say we are interested in number of buses arriving at a bus stand in a city or town. So what is the frequency of these buses they are entering into the bus station per hour, let us say, and how will express them as part of the distribution for analysis. So this is where the Poisson distribution comes into the picture. The Poisson distribution finds wider application when dealing with the discrete events over a given interval of interest. It could be 10 minutes, it could be 1 hour, it could be it could be 2 hours, 5 hours. So we want to analyze because you know that in city planning or something, it is required that what is the traffic, and that can be done very well with the this kind. Or suppose the other problem could be we are having a pipeline, number of defects, how you will encounter in that one in per feet length, or what is the frequency of those things. So this distribution is very useful there. It is a natural choice for analysis when the probability associated with the discrete event is very low. Okay. Take the case of piping analysis. When the analysts are trying to model the defect density, or to be precise, pitting corrosion related to this thing characteristic, then we use this distribution. Other examples of the defective units produced are number of accidents in certain types of process or industrial plants. Let the random variable x represent the number of independent event of the interest. It could be So our random variable, as I can see, and x is x, and it can occupy any value x here over here. So that is what we have, and Poisson probability distribution has one lambda. Again, like exponential distribution, this also has a one parameter lambda. The PDF, and here instead of calling it failure rate, we will say event frequency. You know, otherwise in PRA, probabilistic risk assessment, lambda term is associated with the failure rate. The PDF for x occurrence is given as. So how many events will occur x? Two events will occur in a period of time, or we can get the probability of the event is equal to lambda raised to power x event rate per raised to power x exponential minus lambda and the factorial x. Here lambda is nothing but expectation of x in the is the expectation of x. That means what is the rate of an event occurring, whether it is a defect or an object or any outcome. Okay. So that we give over here. It is written in terms of expectation of x. This expectation term is used a lot in statistics. Sometimes we equate with the lambda. Here it is with the event. It could be failure per unit time or number of corrosion defects in a nuclear plant per feet. So unit could be anything, but what is more important is the event we are focusing on, whether it is a defect or whether it is a entry rate of a buses or it is retrofit modeling. This distribution is used to characterize the corrosion related defects in pipeline and network and all that. So Poisson distribution has got a wider application, more in analyzing the health of the pipeline and network of pipeline sort of functions. So in this week we saw the normal distribution, Gaussian distribution, log normal distribution, exponential distribution, and of course Weibull distribution we have covered here. So the four: normal, log normal, exponential and Weibull. And then discrete we have taken a binomial and Poisson distribution. If you are interested, you can see more distribution, but in probabilistic risk assessment, my assessment goes if we learn this 6 distribution, we have to add Weibull also. It serves our purpose. And in the next lecture, again we will take this topic, and we will have a PRA and statistics estimation.